Welcome to this explainer. Today, we're unpacking the totally hidden yet absolutely crucial world of materials science and engineering. Every single object you touch is hiding invisible structural secrets, secrets that literally dictate the boundaries of modern life. So we're going to look past the surface of the everyday things we rely on, explore the fundamental rules governing how materials behave, and see how manipulating those rules makes our entire advanced civilization possible. Okay, let's dive right in. Picture this. What if we just stripped away every engineered material from your daily routine? Seriously, take away the car you drive, toss out the cell phone in your pocket, the computer on your desk, and even the refrigerator keeping your food fresh. Without the deliberate engineering of materials, we wouldn't just be slightly inconvenienced, our lives would look essentially identical to our Stone Age ancestors. No highly refined metals means no way to harness electricity. No purified silicon, say goodbye to storing digital data. Virtually every single leap in human progress is governed by the specific materials we can figure out how to manipulate. In fact, human society is so intimately tied to manipulating these substances that our earliest historical epochs are actually named after them. Starting with the Stone Age around 2.5 million BC, early humans had a super limited toolkit, mostly naturally occurring stuff like stone, wood, and clay. But look at the leap to the Bronze Age and then the Iron Age. That wasn't just about finding cooler rocks. It was the birth of true processing. Our ancestors realized that by blasting elemental substances with extreme heat or mixing them together, they could force nature to yield superior properties that didn't exist organically. They started altering the fabric of the world. And today, well, we don't just accidentally alter things. We intentionally design them from the atom up. So here is our roadmap for the rest of this explainer. We've just explored a world without materials. Next, we'll look at science versus engineering, zoom in on the scale of structure, cover the 6 material properties, and finally tie it all together with the grand material paradigm. Let's keep moving. All right, part 2, science versus engineering, the why and the how. Because while these subdisciplines are incredibly close cousins, they are asking two fundamentally different questions. To really ground this, just think about everyday beverage containers. We've all got these sitting in our fridge. An aluminum metal can and a polymer plastic bottle. Both are designed to hold pressurized liquids safely, right? Yet they are fabricated from completely different material classes. This is a perfect example of the core difference in the field. Material science is all about investigating the why. Why does that aluminum can crush permanently when you step on it, while the plastic bottle kind of bounces back? It all comes down to uncovering deep structure-property relationships. Aluminum has this sea of highly mobile electrons, whereas plastic relies on a tangle of long-chain polymer molecules. Materials engineering, on the flip side, takes that foundational science and asks how. How do we design the internal structure of a material to get the exact properties we need for a specific product? Basically, the scientist discovers the why, and the engineer designs the how. Though, honestly, most experts bounce between both. Okay, so to understand the why behind these behaviors, we have to change our perspective and zoom way, way in. Enter the scale of structure. The big takeaway here is that a material's structure happens at multiple descending levels. We start up top with the macrostructure, stuff you can see with the naked eye. Drop down a level, and you need a microscope to view the microstructure, which reveals crystalline grains and tiny defects. Shrink even further to the nanostructure, under 100 nanometers, and this is where wild quantum effects start to kick in. Down another level, we have the atomic structure, how individual atoms form specific molecules or crystal grids. And finally, the absolute foundation, the subatomic structure, the incredibly complex dance of electrons orbiting within individual atoms. Every single level plays an integrated part in how a material ultimately behaves in the real world. Which brings us nicely to our next section, 6 material properties, and how materials respond when they interact with the world. Now, before we list them, let's make sure we're on the same page about what a property actually is here. It's simply a material trait, defined by how it responds to a specific stimulus. Basically, how does it react when you provoke it with force or a temperature change? And the vital thing to remember, this is totally independent of shape or size. A chunk of iron has the exact same baseline magnetic properties, whether it's forged into a massive anvil or drawn out into a teeny little paperclip. So virtually all important solid material traits fall into 6 categories based on their stimulus. Think of them as a series of active questions we ask the material. First, mechanical. How does it handle force? Does it bend or fracture? Second, electrical. How does it respond to an electric field? Is it an insulator or does it conduct perfectly? Third, thermal. What happens when exposed to extreme heat? Fourth, magnetic. How does it respond to a magnetic field? Fifth, optical. How does it interact with light radiation? And finally, deteriorative. Basically, how does it hold up against its environment over time? Think rust and chemical corrosion. Let's actually look at that optical category in action. You've got 3 solid disks here, all subjected to the exact same stimulus, ambient light. Yet, their internal structures cause wildly different responses. The first one lets light pass straight through. It's transparent. The middle one diffuses the light internally, translucent. And the third block just absorbs or reflects it entirely, totally opaque. It's a beautifully simple visual way to see how internal structure dictates a physical response. All right, time for our final concept. We've seen the macro, the micro, and the properties. Let's tie it all together into the defining rule of the whole discipline, the grand material paradigm. This sequential flow dictates the entirety of the field. Here is how it works. How a material is processed directly determines its internal structure. That resulting structure universally dictates its properties. And finally, those properties define its performance in the real world. Processing leads to structure, structure to properties, and properties to performance. It's an unbroken chain. Let's use a practical example. If you heat treat a piece of steel, that's the processing phase, you fundamentally alter its crystalline grid, changing its structure. That new, tightly packed structure makes the metal significantly harder, that's the property, which ultimately allows it to perform flawlessly as a highly durable engine part. Boom, cause and effect. As we wrap up this explainer, I really want to leave you pondering that exact chain of cause and effect. Figuring out this structure-property relationship over the last century has allowed us to leap way past our historical constraints, giving us the custom glasses, advanced plastics, and carbon fibers that make modern life possible. But materials science never stops moving. So the next time you pick up a plastic bottle or your smartphone, ask yourself, what totally new structures are engineers processing at the subatomic level right now? And how are those newly engineered properties going to completely reshape the world around us? Thanks for joining me, and stay curious.